if you may recollect, the subject that we have been talking about before this, there has been some gap now, was digital demodulation, right? And specifically we are going to look at a very important component of, we are in the process of looking at a very important component of digital demodulators, which we call the matched filters. Just to quickly recapitulate for you what we have been talking about so far. This is just a very quick review of what we have talked earlier, because there has been some gap. The job of the demodulator is to convert the received noisy waveform into a stream of symbols or bits which were initially transmitted, right? And to cut the story short of our last time's discussion, the way we said this will be done is to pass this noisy signal that you have through an appropriate filter such that it will pass as much of the signal as possible and reject as much of the noise as possible. And since ultimately we are only interested in each interval, symbol interval, the detection of that symbol, whether it is this value or that value, we need to sample this output at a specific time instant, and it is at that time instant that we would like the signal to noise ratio to be the largest, right, at the sampling instant. And after this is sampled, we pass it to a threshold at that specific time instant. Rather, we compare it with the threshold and then decide whether this value corresponds to a particular symbol value or some other symbol value, right? This is the approach that we have to that we have decided to follow, and the crucial component in all this is this filter GT, right? Because it is the job of this filter to produce an output which, when sampled at a specific time instant, will contain most of the contribution from the signal and as small a contribution as possible from noise, right? So basically that's the important thing we need to look at, how to design such a filter. And we therefore went through some little bit of exercise as to what this filter does to the signal and noise that is coming along, right? The specific problem that we have presently decided to work on is the detection of a pulse in noise. We are not even looking at the complete digital communication problem here, right? We have simplified our problem of interest to that of finding out whether or not a pulse exists in a given interval of t seconds, right? Because once we know the answer to this question, how to solve this problem, we can extend it to the demodulation of sequences where we may have multiple valued sequences possible in a given interval. For example, a pulse could have multiple amplitude levels, it could have different shapes, we could take care of all those things. But to start with, to simplify the discussion, the detection problem we are looking at is a very simple one. You have a pulse coming along with noise, but you are not sure, let's say, whether this pulse exists or not in this interval of t seconds, and you want to detect whether what you are receiving is contains only noise or contains that pulse and noise in the presence of noise. So this is the process, and this is the problem we are looking at. Therefore, what we do is we start by looking at the output of this filter in terms of the input Vt, which in the presence of signal will be consisting of these two components, right? The signal will be AST plus NT. When passed through the filter, we will get an output which is a convolution of these two. We have gone through these derivations before. I am just repeating for you to quickly recapitulate. And therefore, when the signal is coming along with noise, we have really at the output of the filter contributions both from the signal as well as from the noise, right? The contribution of the signal comes in the form of the average value of the output, because the average value of noise we have assumed to be 0, right? So the average value of output will obviously correspond to the signal which is deterministic, right? Because it will be essentially equal to this component, whereas the average value of noise will be 0, right. So therefore, to look at the signal contribution, we look at the average value, but to see the effect of noise, we have to look at the variance of this output around the average value, right, because that is the uncertainty associated with the output value, and that will be somehow dependent on the second term, the noisy term, right. So we will therefore like to look at both the average value of ut, which contains information about the signal, and the variance around the average value at the sampling instant, which contains information about the how much noise has managed to pass through the filter, right, essentially that.
RT is a convolution of GT and ST, constant term, first term.
RT is the, yes, ART represents the first convolution, right. That's a because average value of ut will be simply the first term, right, which I am denoting by RT. So RT is the average value of or expected value of ut. Fine. Okay. And I think if you go through the steps that we went through, we finally arrived at an expression for RT, which was this, which is of course very straightforward, which is a basic point, and then through a little bit of manipulation and the assumption that we'll take T0, the sampling instant, to be 0, right, just for the it can be really arbitrarily chosen. Only thing is, depending on how you choose it, you will either get a causal filter or a non-causal filter. At the moment we will not worry too much about that aspect. So depending on where you select your T0, you will either land with the causal filter or a non-causal filter, but just to simplify things, let's say T0 is equal to 0, and then essentially your sample value at T0 equal to 0 is either this, or in the frequency domain by Parseval relation is this. This is the point at which we had stopped last time. I had to go through all this because there was some gap, and I thought we should all be we should all be where we were quite nicely, so that we can proceed from there onwards. Okay, so this is an expression for, this gives us an idea about the signal contribution to the output average value at t equal to 0 or t0 equal to 0, the sampling instant chosen to be 0, right. We like to now look at what is the corresponding noise contribution in terms of noise variance, because that will help us to write down an expression for the signal to noise ratio. We will define this squared value as the signal power, right, the squared value of the mean as the signal power, and the variance as the noise power, and the signal to noise ratio will be defined as a ratio of these two quantities. The larger this ratio, the better it will be for our detection, right. So this is the point at which we shall start today. As far as noise power calculation is concerned, that should be extremely simple to appreciate. Let's look at this picture again. This Vt contains signal and noise, hence being passed through Gt. Best way to calculate the noise variance at the output of any filter is to simply work in the frequency domain, right. Suppose this noise has a power spectrum NF, alright. Then what will be the power spectrum of the noise coming out of the filter? The input power spectrum multiplied by GF mod square, right, and the variance of the output noise will be simply the area under its power spectral density function, right. Whatever the power spectral density function of this noise, the variance of noise, which is the total power of the noise, total average power of the noise, is nothing but the area under its power spectral density function, right. So the most convenient way of writing down this expression is to go to the frequency domain and write sigma square directly as equal to, first we write down the expression for the output power spectral density function, which will be NF, which is the input power spectral density function, multiplied by GF mod square, and the area under this density function, which is the integral of this quantity, is the output noise variance. So that's very straightforward. So we now have an expression in the frequency domain for signal power, output signal power at the sampling instant, an expression in the frequency domain for the output noise variance or noise power. Do you all agree with this? Is there any doubt about any of these computations? We can therefore set up an expression for the signal to noise ratio by defining this to be the representative of the signal as A times R0 mod square upon sigma square, which then obviously is the ratio of these two quantities. Okay. All right. And our job is to choose a filter transfer function GF. What is the function which is under our control, or which we want to fix? It's a filter, right? So we want to optimize this transfer function GF so as to maximize this. Ideally, what we would like to have is a filter which will completely eliminate the noise and pass only the signal, but we know that will be impossible. Why? Because the signal and noise spectrum partially overlap with each other, isn't it? The noise spectrum may be wider, but there is some amount of noise present in the same band as the signal is present, right? So it will be impossible to eliminate both of them, eliminate noise completely and pass the signal only, right? So at best, the best compromise we can hope to get is maximization of this quantity, which will be a useful thing to do. All right. So let's therefore write down this expression in detail and see what we can do about it. Before I do that, I think that much is clear as to what this expression will turn out to be. To do this maximization, it's clear what we have to maximize. We have to maximize the ratio of these two quantities with respect to the function GF, right? Now this is a slightly different kind of maximization or minimization that you might have done in your calculus. Have you done a calculus of variations? No, you don't know. You're not familiar with calculus of variations, which tells you how to maximize functions of functions, right? Because here is a function signal to noise ratio of a function GF. We have to choose a function GF so as to maximize this parameter, right? Now that's a slightly different kind of area in mathematics, and since we are not that familiar with it in your class, we will not use that. We will use a different result, which is a very simple result, and I will not prove it. I will just state that result from maths. It's known by the name of Schwarz inequality. Are you familiar with Schwarz inequality? Okay, so that's no problem then. Where have you used it?
Last inequality.
In what context did you use it?
Just in general.
Just as a result by itself. Okay, so all I need to do is recapitulate what that result is for you, and then we will see how that is very useful in obtaining the derivation of our match filter, right? Or in doing the maximization that we want to do. All right. This result is as follows. Suppose we have RT. So let RT and ST be our finite energy pulses. Right? They may be complex signals. Both RT and ST may be in general complex. They may be real valued or complex valued. Then this result holds. Take magnitude of RT square, integral of this function with respect to t multiplied by st mod square dt integral of this. This product is always greater than or equal to the integral of r conjugate t st dt.
Square. Whole square.
Mod square. Thank you. Okay. With equality, do you remember when are the two sides equal? If and only if, well, RT is a constant times ST. A scaling factor doesn't matter, right? Right? So the two sides will become equal if that is clear. In other words, suppose I take the ratio of this upon this. I take this to the right hand side. Okay, I'll come to that a little later. So that was a statement of Schwarz equality, and we'll like to now use this to do the maximization that you want to do. Remember, this is our starting point. We are interested in setting up the ratio S by n from these two expressions. Now let me write down this expression. S by n will be mod A integral GF SF df square upon nf times now. Do you see how to apply it here? Not so obvious.
Numerator is
Hmm?
break down the numerator.
Some manipulation is required before you can apply it straight away, because you have to identify functions.
NF has to be taken as n by 2 also.
Yes, that is true. So we can write it as mod A square what we'll do is we'll rewrite the function here. See, the approach is the following. We'll identify this as what?
One function.
As the product function RT ST. Okay? RT ST, and we have to find out, we have to then, sorry, this is one of the functions where this is a product function. This is the product, we have to take this as a product function and this as one of the functions, and therefore we like to rewrite this in terms of that product, right, with this as the square of one of the functions. This is square of another functions, right? So we'll write the square root of this into GF into SF upon right df mod of this whole square, and obviously you can write this as root NF GF and now you can see the connection between Schwarz inequality and what we want to do. Okay, it's nice if I could have kept both of them in front, but I think only one of them I can show at a time. So I have constructed one of these functions. This is in the denominator and this is in the numerator, right? So what we are saying is we have the ratio this upon, let's say this upon this. This ratio is going to be less than or equal to a specific quantity, which is this, right? Always. At best it can be equal to this, right? So what is the maximum value of this ratio?
The two functions become equal.
There are two things. One is at what point is the maximum achieved, another point is what is the maximum value, right? The point at which maximum is achieved is when this condition is satisfied, right? And the maximum value is, maximum value of the ratio is well, whatever this is. Alright, so these are the two things. First let's look at the maximizing point, right, the maximizing function. the condition under which this ratio will become the largest, which is what we want to do. We want to maximize this ratio, right? The condition for that is that, let me write down. This quantity is a constant times this quantity, right? Actually not. Some other. See, the original result is R conjugate TST. So the conjugate of this quantity should be equal to a constant times this quantity, right? Or in other words, GF, maximization will be done for GF equal to SF, S conjugate F upon NF is a real function. Why? Why NF is a real function?
The model we have assumed. We have assumed a
So
constant.
noise is very
White
constant,
noise.
sir.
No, it's a power spectral density function. A power spectral density function has to be real, right?
Noise power.
NF represents a noise power spectral density function. Any power spectral density function has to be a real positive function, right? So that is why in fact we can talk about a square root, otherwise we can't even talk about a square root, right? So it will be what is this? This is the function GF which will maximize this ratio. How does it come? It comes from the condition that the conjugate of this or this function should be the some constant times the conjugate of
The
this.
denominator you got only one of the product terms.
Why not two integrals?
So basically it is the product of two integrals, that RT square integral and multiplied by ST square.
That is what I try to explain to you from this basic result. I'll take one of these here, right, which is then there is a perfect matching between this and this. All we're saying is that this ratio is less than or equal to certain quantity which is a constant which depends on
We
ST.
are not talking about the actual quantity. I mean, that will
We are not talking about the what the value is,
maximum value will be the other functions squared.
right? Right? We are not looking at the maximum values yet. We are looking at the condition under which this maximum will be achieved. Right? That condition will be this condition, RT equal to KST. We identified what is RT and what is ST. Right? We have identified in this what is which corresponds to RT, which corresponds to ST. Right? And then we are using that fact in arriving at this result. Is it clear?
You put SF conjugate over here.
Yes, why? Because this result here says R conjugate TST, right? So one of them has to be identified as a conjugate function, the other as a unconjugated function.
Yeah, because root NF,
I have combined that.
root NF conjugate.
Actually, root NF at GF is equal to S conjugate F upon root NF. And then I have taken root NF to the other side, and finally we get this result. Okay? So, this is the expression for the filter transfer function which will maximize the signal to noise ratio at the sampling instant t equal to 0. T0 is equal to 0. T0. Alright? And the maximum value of the signal to noise ratio is obtained from the fact that this is going to be less than or equal to well, now we can do that. Maximum value we can obtain by substituting this in this expression. This transfer function will maximize the signal to noise ratio at the sampling instant t sub 0 equal to 0. The maximum value of the signal to noise ratio can be obtained by substituting this expression for GF over here in this expression, and that you can easily check will be simply equal to SF mod square upon NF. Okay? And the interesting result that you will see here is that the expression for the signal to noise ratio therefore obviously does not depend on GF, right? So maximum value of signal to noise ratio is it's a maximum possible value and it's independent of GF. Of course, it has been derived from the fact that GF has taken that specific value. Yes, please. All right. There is a.
In this, there is just one expression in denominator, but the expression you wrote for the Schwarz inequality, there are two expressions. There are two integration of two products. So how do you equate those two?
This is one of the functions, and this is the other function.
Yes, also right. Now in the denominator, there's just one function.
Correct. The other function is still on the left hand side. Right? We are looking at this ratio, right? And we want to find out under what condition will this ratio be maximum. What the Schwarz inequality tells us is that this numerator quantity is less than or equal to this into the other quantity, right? Therefore, this upon this is less than or equal to that other quantity. All right? And therefore, this is what we need to maximize. We don't have to worry about what the other quantity is, right? And the point at which this maximum will occur is this point. All right? It's on the right hand side, not on the left hand side. I said it is on the left hand side. Okay. Fine. Now, let's look at this equation again. Suppose I want to change the condition to, I want to eliminate the condition that T0 equal to 0. What modification in the result you will notice? So our optimum filter is some constant times S conjugate F upon NF
SF will get modified to some term.
e to the power minus j2 pi F T naught, right? This will be the additional factor we have to consider if we want to maximize the signal to noise ratio at some arbitrary time instant T sub 0 rather than equal to 0. Right? Okay? Okay, now let's look at, before I do any discussion, let me show you the picture that we have in mind. Here is your signal coming along with noise. So the noisy signal is coming along. We pass it through this filter, which is, whether we put the scaling factor there or not, it hardly matters, okay, because it will not affect the signal to noise ratio, right? The scaling factor will affect the signal and the noise in the same way, so we will not bother about it. We will sample the output of this at whatever sampling instant we need, t equal to 0 or t equal to t sub 0, right, and threshold it, that is compare it with the threshold, this value, and then decide whether the pulse was indeed present or whether the input signal contains only noise. Okay? If the value, output value is below a certain threshold value that you have decided earlier, then you can say that there was no pulse present. If it is above that value, that we can say with some level of confidence that it is due to signal, right? This output is due to the signal. Therefore, the complete receiver design, really speaking, not only involves using this kind of a match filter, but also deciding on a suitable value of threshold, because that is going to affect your performance quite significantly. If you choose, for example, too high a value of threshold, what is likely to happen? Sometimes when the signal is indeed present, because of noise, the level may be less and you may wrongly decide that it is absent, right? On the other hand, if you choose too low a value, a noise spike might come along. There will be nothing else but noise, and sometimes because the noise is sufficiently large, because occasionally it can be large, it can produce at that sampling instant a value which is sufficiently large to exceed the threshold, and thereby causing a false decision that a signal is present, when indeed none is present. So we have the false alarm probabilities and the probability of missing a pulse, and these are kind of dependent on how you choose the thresholds.
Here we have maximized the signal to noise ratio, but we have not maximized the minimized the probability of error.
Probability of error.
We are doing different.
Sort of.
Yeah, you're absolutely right in pointing out that fact. The ultimate performance criterion in a digital communication system is not just signal to noise ratio, it is really probability of error, because that's what we finally. But fortunately, for most problems of interest, one can express the probability of error directly in terms of this parameter signal to noise ratio, right? So if you maximize this effectively, that's equivalent to minimizing that probability of error. We'll see that when we take up digital communication problems in particular, right? Right now it was a general problem. And basically I wanted to introduce to you the concept of a match filter, which is an essential component in the demodulator. Now let me just do a very brief discussion and make you appreciate how this really functions, how this match filter, so-called, actually this is what is called a Whiten match filter. Strictly speaking, this function is called a Whitened match filter, right? But I'll elaborate on why it is so called a minute later. First of all, how it works. Let's discuss how it works, or how it does, how it maximizes signal to noise ratio, or why it maximizes signal to noise ratio. Intuitively, we can try to appreciate that. Basically, what you'll notice is that the transfer function will have large values at those frequencies where the signal to noise ratio is large. It will have small values at those frequencies where the signal to noise ratio is poor. Input signal to noise ratio is poor, right? So basically, what a match filter is really doing for you, or a Whiten match filter is really doing for you, is weighting the input signal in the frequency domain according to signal to noise ratios present at different frequencies. Components which have most contribution from signal only are highlighted, are given more weightage, and components which are more noisy, those frequency components which are basically getting information from noise, or which basically contain energy from noise, are the ones which are suppressed. Okay, so you basically choose a weighting function or a transfer function which depends on the input signal to noise ratio at different frequencies. That's the basic idea. And the reason why it is called a Whiten match filter is simply this, that I can think of this operation as a cascade of two filters. One is this, and the other is this, as if I had two transfer functions, right, in cascade, like that. If you just think about it, if you look at this output here, let's say the input contains only signal, only noise. What will be the power spectrum of noise here? It will be constant, equal to 1. It will become white noise here, right? So whatever noise is present is whitened here, and then of course if the signal is also present, that also gets modified to some extent, and then we pass it through a filter which is really matched to the signal itself, right? So we call it a Whitened match filter. This is just a term. It doesn't really, it comes from this kind of a interpretation. All right. Let's take the specific case when your noise to start with is white Gaussian noise. We already assumed it is Gaussian, but we are now making a further additional assumption that your input noise itself is white, right? What does it mean? That NF to start with is equal to some constant, say equal to N0 by 2. All right. Then what will be your optimum filter? You substitute that here. It is C times S conjugate F upon N0 by 2. And since N0 by 2 is a constant, you can combine it with this constant C. So essentially it is equal to S conjugate F e to the power minus J2 pi f t0. Alright. So in this case, the filter that you get is GF. I'll forget about the constant. It's simply equal to S conjugate F, and if I take T0 equal to 0 again, that is all there is to it. Right? This is really what is called a matched filter. Right? The other one is Whiten match filter. It's more general. The Whiten match filter is obviously more general than the match filter, right? Because this is for a specific case when noise is, input noise is white, right? Okay. The next thing we like to do is write an expression for the output signal to noise ratio, which is S by N, which will be essentially equal to A square by sigma square, because we are assuming that your signal is AST. Let me write down. If your signal is AST such that ST is of unit energy, then this is equal to A square. And noise variance output is sigma square. Now, we have an expression for this already here with us. For the general case, this was the expression. If I put NF equal to N0 by 2, then what will I get? That will be simply A square, this will be A square by N0 by 2, right? Or 2A square by N0. I think a better expression to write is, let me denote this, we can think of as signal energy in its time interval. Suppose the signal is of duration t, pulse is of duration t, this A square is nothing but E sub p. Alright? If provided integral S square t is 1, we are assuming that the integral S square t is 1, or whatever ST may be, finally let us say this energy is E sub p, then this is simply 2 EP by N0. Anyway, this is the expression I wanted to really write. And there are some important lessons to be learned from this expression and from the previous expression for signal to noise ratio. Let us see what these lessons are. Is this okay?
This is the signal to noise ratio.
This is the
input to the last filter. Because that time the noise is N0 by 2. So that's what you have taken.
This is at the output. I have computed the signal to noise ratio.
Okay. In general, this is not therefore a particular. We are not doing a particular case of white noise input.
No, let me. Okay, there is some confusion. This is the expression for the signal to noise ratio in the general case, right? At the output, of course. I should remove this and say equal to when you are using a match filter, right? When I take the case of white noise, NF becomes equal to N0 by 2, and this is really A square integral SF mod square, which is EP, right? So it becomes 2 EP by N0. So I have two expressions, one the general one and the special one for the case of white noise. Let's look at the special one first. What you'll find here is that this output signal to noise ratio, once you have used a match filter, does not even depend on the pulse shape. Do you appreciate that fact? It only depends on how much energy is contained in the pulse. Right? The specific pulse shape is of absolutely no consequence in the determination of the output signal to noise ratio. Whereas that is not the case if your noise is not white. You can see that. In this case, the output signal to noise ratio depends on the pulse shape also. It depends as much on the power spectrum of noise as on the pulse shape itself. So the pulse shape itself is of little importance in situations where we are mostly dealing with white noise, and that is the general situation for us in most communication applications, right? Because the noise is sufficiently broadband so as not to worry about the specific pulse shape. However, we have already seen that pulse shape is important for us for other reasons, like for example intersymbol interference, right, and things like that. So in any case, it is nice to know that we don't have to worry about pulse shape as far as performance against noise is concerned, as long as we make sure that there is no intersymbol interference, and as long as we give sufficient energy in the pulse to have a good signal to noise ratio. The only parameter that is really of importance is energy contained by the pulse. Okay, let me write down an expression for the match filter in time domain. We start with GF equal to S conjugate F. What will be expression for GT? Can you straight away tell me?
S of minus
Yes, S of minus T.
S of minus T.
Or will it be S conjugate minus T?
No, S of minus T.
minus T.
It will be S of minus T.
In general, if the signal is complex, this is what I wanted to check.
It is S of minus T.
No, let's okay. Since there is some confusion, let's work it out.
In general.
From here to here,
Yes, in general.
from
maybe
Fourier
it-
transform properties.
Yes, sir.
It is fine.
In general, it is.
Then what is what was the special case you are referring to?
The real.
The real signal.
Yeah, but we are here considering general
Oh, real
signals.
signal.
Okay. So do you want me to do it, or do you think it is okay? Fine. So and if I want to generalize it further and make the sampling instant arbitrary rather than t0 equal to 0, how will it change? Suppose I want to introduce a non-zero value of
T naught
t0,
minus T.
right? Here it will be multiplied with e to the power minus j2 pi f t naught. The corresponding thing here will be, this will become S conjugate t0 minus t. Is that okay?
Minus T0 minus T0.
No,
Well,
no.
minus T minus T0.
No, so T naught minus T.
Minus T plus T0.
This corresponds to,
That corresponds to a delay.
Minus T plus T0.
हाँ तो T naught minus T.
yeah, so minus t plus t0, which you can write as t0 minus t. Okay. And so that's the most general expression for the match filter in time domain, and that's in the frequency domain. Let's take a few examples. Now, before taking example, a few other remarks. So first remark, if you remember that the for the case of white noise, output SNR depends only on pulse energy, right? Second important point is the nature of the match filter output. By considering the output, let us say at time instant 0 again, what will this be? Your impulse response is, let me write down the general expression first. ut is equal to, output is input or impulse response is S conjugate minus zeta into input is Vt, or so Vt minus zeta, right, d zeta. Convolution between the input and the impulse response. Impulse response we have seen is S conjugate minus zeta, the match filter impulse response, right? Just using this expression, Gt is equal to S conjugate minus t, all right? At t equal to 0, what will happen? This is the sampling instant. Suppose we chose this as a sampling instant, because this corresponds to sampling instant t0 equal to 0. This will become S conjugate minus zeta, t is equal to 0, so V minus zeta d zeta, which by a change of sign of the change of variable in the integral here can be simply written as S conjugate zeta V zeta d zeta, or VTST S conjugate t. What is this quantity? What kind of operation you are performing now? The correlation between the received signal and a replica of the transmitted signal, right? Dipankar, where is the confusion? Yes,
No, that's all right.
because you are changing the okay. So what does it tell us? That the output of the match filter at the sampling instant, this is a very straightforward expression, but the significance is that the value that you are sampling and based on which you are going to take your decisions can be regarded as having been obtained by correlating your received signal with a replica of the transmitted signal, right? So you could as well replace your match filter for the purpose of the demodulation by a suitable correlator. Is it clear? Whose job will be to multiply the received signal with a local replica of the transmitted signal, right, and integrate between the over the duration of this, let's say between 0 to t or whatever, and then sample it at that instant. Okay, so you can replace the match filter with a correlator. We'll talk about this point again. So this is nothing but the correlation between the received signal and the pulse shape ST. So basically match filter helps you to calculate this correlation. In fact, if you were asked to describe the nature of the match filter output in terms of its waveform, we can now say something about that. Let's talk about ART, the mean value of the output, right? Only the mean value. We're not looking at the noise contribution, we're only looking at the signal contribution. Suppose I had only a signal of shape ST feeding the match filter, output will be obviously RT, the mean value, because there is no noise, right? Then that is going to be equal to, we have just seen that, alright, I made a change of variable, right? I am rewriting that again, which is nothing but, is this expression familiar to you? ST is the autocorrelation function of ST. Okay, so is proportional to the ACF of ST. The match filter output, when the input is only signal, the pulse shape to which it is matched, right? will produce an output which is nothing but the autocorrelation function of the input waveform. And where are you sampling this autocorrelation waveform? At its peak value, which corresponds to 0 lag. Right? Basically that's what you are doing. The match filter, for the case of situation where the input we have only signal, produces an output which is nothing but the autocorrelation function of the input signal. Right? Because the impulse response is matched to the same signal. Alright? So finally, I'll end up this discussion by just discussing a few cases of match filter. These all cases are for real signals. Here is a situation where this is your pulse shape. Right? Let's say from 0 to t. Then the match filter will be alright. It depends on where you select your T0. I have selected my T0 equal to T. How do you obtain the match filter? Impulse response. You first, the same operations that you do in convolution. First reverse the time axis. So this will go here. Right? And then shift it by T0. Whatever it is. So if I have taken T0 equal to T, this is what it will look like. Okay? For a rectangular pulse of this kind and T0 again equal to T, you will again get the same rectangular pulse as the impulse response of the match filter. Right? So this is your ST, this is your corresponding match filter. Of course I am considering here only real examples. Suppose I had taken T0 equal to 0, what would have happened? What would be the impulse response of the match filter? Essentially the same. In shape it is the same. Only thing is it is non-causal. That is why it is best to choose T0 equal to T. In fact, this is the optimum value in a digital communication environment, because every T seconds you are sending a new pulse. Right? So you better therefore choose a sampling instant equal to or at the end of every pulsing signaling interval. Right? This is what is typically done. So that's why a match filter based demodulation is really a symbol by symbol demodulation. You look at one symbol at a time, sample the output at the right instant, and in fact that is a theory that we used even when we discussed Nyquist pulse shaping, because we assume that we are going to look at the output of some filter, which in this case is nothing but the match filter, every t seconds. That is why we wanted the output pulse shape to be such that there are regularly spaced zero crossings every t seconds.
So in the case of where suppose Emery,
Same thing.
You have then M filters.
No. That will depend on the specific kind of Emery signaling you have. We'll discuss.
Suppose we have got M different pulse shapes.
You will have naturally.
If you have M different pulse shapes, yes, then you have.
You're going to have
Yes,
M
but
filter.
not all Emery systems use M different pulse shapes. Okay, so you have to be. We'll see all those things. We are only looking at the basic match filtering theory here, but the next thing will be application of this to digital communication. We're going to look at all those things. Let's take a third example where I have deliberately chosen a pulse shape which goes from 0 to infinity. Right? Now, how do I choose a match filter? There is a problem here. You can see that, isn't it? Particularly in choosing a value of t sub 0, such that the filter will remain. It doesn't matter. I can always choose any t sub 0, and the proper match filter will, of course, suppose I choose t0 equal to some value t, right? The proper match filter really is this. It is non-causal, right? It extends into the negative time axis and goes on and becomes 0 at t0 equal to 3. But obviously, if I want to make it causal now, there is no way out but to choose a sufficiently large value of t sub 0 such that what I am ignoring when I do the causality approximation is the tail of the impulse response, right? This tail of the impulse response, so that it doesn't have significant energy, right? So in this case, what I have plotted here is, you can say, some kind of an approximate a match filter rather than an exact match filter. Right? So I think this is where we stop today, and we'll next time see how do we invoke or use the match filtering theory in designing demodulators for different kinds of modulation schemes that we have considered earlier. Okay? Thank you.